presentation will be given by Pavel Pudlák on implicit proof systems.
Thank you. Thank you for inviting me for this workshop. So what I'm going to talk about is not in the mainstream research in proof complexity. Mainstream research is in weak proof systems, and people are hoping to prove lower bounds, and people are applying proof systems for understanding SAT solvers and so on. But if you want to really understand the problem P versus CoNP versus NP, or proof systems in general, then we have to study also strong systems. The strong systems naturally appear in connection with theories, which I will mention in a moment. But we would like to have some combinatorial characterizations of these strong systems. And therefore, it would be good to start with something that is more combinatorial. The concept of implicit proof system is something that potentially can be used. It was introduced by Jan Krajíček already almost 20 years ago. And it's a very natural concept. So it's the idea is that we may have an exponential size proof, but the proof can be presented succinctly in the way that you have a circuit which produces bits of the proof. And in this way, we have something like a proof. So why not to consider this? But there is an important thing that we have to realize, that we want to get a proof system in the sense of Cook-Rekov, which means we should be able to test whether this exponential large proof is actually a valid proof. So you get a circuit, and now you don't know what the circuit does. So you cannot just print the whole circuit because it's exponentially large. So there is this extra condition that we also need a proof that the circuit is a concise version of the proof in the system P. In this definition, P is used for both, that is for this implicit potentially exponentially large circuit, and for proving that this circuit is correct. But one can also study the situation where you use different things. For instance, you could just use one system like extended Frege, and then for all implicit proof systems, just increase the second, increase the first thing and keep D to be extended Frege. And we don't know whether this would be a weaker concept. So it just shows, so this fact that we don't know just shows how little we know about this concept. And there is one problem. It's a very nice definition, but there is one problem with this definition. We always think about proof systems not as a particular algorithm, a particular code that we get, but as a class of algorithm, all things that are polynomially equivalent. And now for this concept of implicit proof system to be reasonable, we would like to do the same, but it is not obvious that if we have two proof systems which polynomially simulate each other, then also the implicit proof system would simulate each other.
I have a question.
Yes.
The proof is supposed to prove a small CNF, or is it supposed to prove an implicit CNF?
No, we just take small CNFs. The CNFs are not implicit. They are. So that's why I'm saying that it's like having an exponentially large proof, but exponentially large proof of something polynomially large. Yes.
So this is a very naive question, but is it clear like how the proof system reasons about the correctness of the circuit? I mean, or what the circuit is like from the proof system point of view?
It's not difficult to imagine what it does, because typically the proof is consists of a sequence of formulas, and if you take a standard fractal, you can assume that these formulas are actually small formulas, and then you need to prove that the circuit, if at certain part you have this formula and elsewhere you have this formula, then they have to be connected in a particular way. So it's of course something else if the proof system is not based on formulas, but this is just done by taking this taking the computation and proving that the computation actually is correct, because you encode the computation of the machine that defines the proof system, and this proof system D will prove that locally it is correct. The computation it is locally correct, and the output is what you want. And
so I could think of the circuit as maybe like being this standard Satin encoding, like a CNF describing every wire, and that's what the proof system is going to talk about.
Yes, but certainly it's not so easy to imagine these things and not see what's going on, and especially if you do one more iteration, then you don't know what's going on at all. Okay, so let's. Yes.
If P simulates Q and the the more efficient local simulation of like proof in P can be proof in Q can be translated in proof in P local way, and proof like IP.
You made a simulation.
Yeah, P simulates Q by more efficient.
Yes, so this is something that I don't fully understand, and I want to say more about it. Yes.
For the simulation notion, I guess here P simulation, you mean like where you can translate efficiently?
Yeah.
The one where it's just length one, that would obviously hold or no?
Efficiently. I'm talking about efficiently.
Okay. But for the other one, the answer is yes, that it does carry.
For the other one,
That's just length based.
I didn't think about it. It's a good question.
Because how do you know that if one proof is succinct, the other proof is succinct?
Oh, yeah.
It's going to be more helpful if you have an actual algorithm to switch from one proof system to another.
So, so the question can be stated, or more general question can be stated without referring to the proof system by the following way. So suppose you have a Boolean circuit that defines some string. So the string is defined by the output for all inputs, and we suppose that we order it lexicographically or order like the integers that they represent. And the question is, suppose you have a function computable at polynomial time. Does there exist a function f such that it would produce from a circuit which from circuit C would produce the circuit that would produce the string of what you obtain from the string encoded by circuit C. Is this clear what I mean?
The identity functions.
So you have a polynomial time computable. Yeah. And then you get a circuit, and then the circuit produces some string. Now apply the polynomial time function to a string. You get another string, And the question is, can you produce a circuit that would produce the other strength? This equation. Yeah. So what is the answer? Is it possible or not?
This is probably like, if it's possible, that something like nx equals x or something.
But the answer is very easy. So consider this thing, and obviously, if you can do this for this function, then you would be able to test satisfiability. So it's definable even by a finite automaton, not by polynomial construction, and still you get if n only is p equals np.
Sorry, could you? So, oh, okay. So we're.
So the function does this, it checks the input, and if it finds 1, then it puts at the end. And if it is 0, then it...
Oh, right. Oh, okay. So...
It's taking a string and putting a 0, 1 on the end.
Right.
Okay. So this is a bad news. And now imagine that you formalize something by sequent calculus, and you make a small change. So instead of using this rule, you would use this rule. So that is completely equivalent. And now you produce implicit proof system. So are they polynomially equivalent? Well, considering the previous example, then you are, of course, not sure that they are polynomially equivalent. But, there is also good news. I claim that for natural formalizations, you get polynomial simulations, at least for extended Frege. And the reason for this is the following theorem that Krajicek proved in the same paper, that implicit Frege proof system is associated with the bounded arithmetic, which we denote by B12. It doesn't matter what it is, but the important thing is that for this theory, this theory proves the soundness of implicit extended Frege, and it also proves that if it proves soundness of some proof system, then implicit extended Frege polynomially simulates P. Now, what it means is that if you take some formalization of extended Frege such that you can reproduce Krajicek proofs, then this formalization, you get equivalence of implicit Frege proof. So one has to look into the proof and understand what is essential in this proof, so that we get equivalence. So I still don't understand this. I don't have answers, so this is more like an open question. What are natural formalizations? But the possible approach to this question that I see is to consider reflection principles, because we know the following characterization of polynomial simulations. If we have two proof systems, they suppose that this is stated more generally, but suppose you have two proof systems that are strong enough to prove their own reflection principle, then one proof system simulates the other if and only if it proves the reflection principle. So we don't have to consider any formulas, any proof. We just need to focus on this. And if the reflection principle can be represented in some natural and concise way, then which would be able to lift to exponential size, then we would get this simulation. Okay, so this was just the introduction to implicit proof systems. And okay, so the question is, what happens if we iterate it again? Yes.
More about the theorem?
Could you please?
Yeah, the theorem that you showed on the John's theorem on the previous slide. The D1 proves the sounds natural. You're going to say anything about, can you say something about
On the proof or no? Well, okay, so the let me say anyway. So the point is that the theory is the second order theory above these first order theories, which means that it can argue about sets. And these sets can encode something like exponential large strings. So basically, the natural idea is to unwind this succinctly defined proof into an exponential large proof, and then argue about this exponential large proof. But I will mention something similar in a moment. So my interest into this come from the following question to consider a proof system associated with theories. If you have a first order theory which is say polynomially axiomatized, then you can define a very natural proof system associated with this theory, which is much stronger than the proof system that we associate with fragments of bounded arithmetic. And suppose that this theory is about natural numbers, so we have equality, but it doesn't matter. We just need some predicate that, for which it's possible that it's true or false. So then instead of propositions,
what do you mean by polynomially?
I mean that you can recognize the set of axioms using polynomial time algorithm. So you can take a propositional formula and substitute the atomic formula for each proposition. An atomic formula for each proposition, namely for the ith propositional variable, you take ith first order variable and say that xi is equal to 0. It may be true, maybe not. And thus you have just a formula that talks about some variables to be equal to something, and you can apply logic to prove whether it's the tautology or not. And we assume that we have some say Frege formalization on this. So
what's the PI? What do you mean by replace variable by equation?
Yes, by atomic formulas, which are equations of the form xi equals 0. This is a basic proposition in a more general sense. Okay, so yes, and it's something I wanted to ask you how strong this proof system is, but I turn this. So now you see that it is a very strong proof system, but if you look at it at first glance, you don't see why it should be strong. But one reason that it is strong is even if you don't know this concept of implicit or this theorem, then is the fact that you can use quantifiers. So if you remember, there are these quantified propositional calculi in which we can quantify Boolean, in which we can quantify propositional variables. But now, if you are in first order logic, we can quantify first order variables. So any quantified propositional proof translates into a proof in this theory. But this is much stronger, and even in the proof system, even for the really rudimentary part of arithmetic is extremely stronger. It simulates implicit Frege, and I believe it simulates all iteration of implicit Frege. But I would like to sketch the proof of this theorem very quickly in the remaining 10 minutes. The first thing is to go from Robinson's arithmetic to S12. And this is done by interpretation, because you can interpret S12 in Q, and therefore you essentially can use the power of S12. So from now on, let's talk about S12.
Could you tell us what Q actually is?
What Q actually is?
Yeah.
So Q says that zero doesn't have a successor, that two successors of and so on, and that x plus successor y is successor of x plus y.
Okay.
And for multiplication, nothing else, no induction.
So here you're taking Boolean formulas and replacing the Boolean propositional variables within these propositions.
Can you think of arithmetic minus induction?
There's in Q, there's no induction, yes. No induction at all. But also it seems so weak. You can interpret not only S12, but even stronger theories. And once you interpret them, then you can use them to argue about these propositions more efficiently. So this is one step just to do something more. And another thing is that if you want actually to prove something non-trivial, to argue more efficiently about these tautologies, what we can do, we can pass from this representation of tautologies by simply using these atomic formulas to arithmetical representation. So here, this phi in square brackets means that we take the Gödel number of this tautology, and then we express in arithmetic that it is a tautology, and then we have some arithmetical statement with which we can argue in some sense more efficiently than if we use only something like that, because then we can talk about all things that are tautologies and so on. So this is another step, and then one of the key steps is to show that S12 proves the soundness of implicit Frege in the following way, that it proves that every implicit Frege proof is sound if it is only of logarithmic length. So formally, it means that x is less than a logarithm y, means that the length of x is double logarithm of y. So, or put otherwise, we can prove that proof of the implicit Frege proof is sound if we take the Gödel number and raise to this Gödel number, which will be something exponentially large, then this number must still exist. So we know that S12 in general doesn't prove that for every x there is this exponentiation. So this is indeed something that restricts.
just get a clearer.
The whole thing is already set.
Are the variables correct in what you've written?
Yes, sorry, there is a typo. It should be X. So Y is just a bounding number. Here we should have X. And the idea is, as I said before, that if the proof is small, is on the logarithmic size, then you can expand it, which means that instead of using implicit definition by a circuit, you can really construct the string that represent this proof. And then we have just a regular extended Frege proof, and we know that S12 proves soundness for these proofs, so we can prove that it is sound. Okay, so what remains is to show that if we are given a proof, then we have a short proof that there exists 2 to the Gödel number of this proof. Then we will be done. So in order for a given proof, so we take a proof. So this is stated for a natural number, but if you get a proof, then we need to show by construct a polynomial size proof that there exists 2 to the Gödel number of this proof. And this may seem like a totally obvious thing. If you have a standard number, then 2 to the n exists in every model, not only 2 to the n. Everything exists in a standard model. But we have to prove it actually. And it's not completely obvious. So let's look at how this is done. So what actually is a representation of a number? So we use the binary representation using terms of this form, which gives us logarithmic length representation of the number. And for such a number, we should show that there exists 2 to the value of this number. But it may seem that you would multiply 2, but you would have to do it exponentially long time. So this doesn't work. So what one can use is the following. So this this idea goes back to Solovey, that one can define formula alpha x that defines, it's not stated it defines the initial segment. This is not important, but it can be. That is, in a sense, inductive, that it contains 0, and with every x, it contains x plus 1. But also with every x, if it is satisfied by x, then it is satisfied by 2x. And then, moreover, there exists exponential large y for every x. And once we have this, then we can define. Once we have this, then we can prove in polynomially, like linearly many steps, that such a term satisfies this formula. Using the first 2 properties, we prove in using many steps that it satisfies this. And once it satisfies this, we also know that there exists an exponential large thing. And then we can use
alpha of x from being trivial, not using x at all.
Sorry?
What prevents alpha of x from being trivial, from not being dependent on x at all? the alpha of x is
The last condition.
It doesn't work for this for the period. Just trigger x equals x.
This one you cannot prove it.
Yes, if you deny this property, yes, but you have this property which you can.
for every x, alpha of x is the same thing.
Yes.
And the third property is also not carrying water.
The third property says that for every x,
Oh,
there is this exponential large. So you would prove that for every x there is an exponential large if the formula is true. So this is the whole proof. Let me just summarize. So given an implicit Frege proof with Gödel number n, we can construct in Perlman time a proof in S12 that n is logarithmic, that there is an exponential large number, and then we use the soundness for logarithmic size proofs of implicit Frege. And this finishes the theorem that the strong system of fuel simulates the implicit Frege.
Yeah, any questions?
Of what the strong system is it like infinitely iterated implicit?
Yes, so for my conjecture is that it's infinitely times iterated, and you see that this proof scales out and that you can iterate it, but I'm not claiming it now because you see that there are technical complications which one has to really check and do so. But I just wanted at least this to be clear that you can simulate at least implicit Frege.
And the other direction remains to be proved.
Yeah, also. The other directions is also interesting because it's based on cut elimination, but these are just ideas.
What is the strong system of the empty theory?
The strong system of the empty theory, I guess, is quantified propositional calculus. Well, it cannot be completely empty. You must have a predicate for which you can prove that it's consistent to that because that does not. So essentially, you need something to use for the propositional result. Or maybe you also need the extent that there are at least two elements. But then I think you get quantified prediction. But it's the concept is so general that you can consider other theories that are not and so on.
If we take a simple theory below extended Frege and look at the implicit, do we get extended Frege or something stronger? Because so it seems like you should be able to like simulate some of the rules people were talking about yesterday as implicit proofs.
Yes, sure. Now, Jan Krejcik proved that if you take somebody should help me, that you can take just
Implicit resolution.
So
both proof systems are resolution is EF.
if you start with maybe tree-like resolution, then you get already EF. So these are examples where we positively know that you get something.
If the IP is something teacher resolution and extended for like is it zero first? Does IP become something between extended and IP? or it's just about the
Could you repeat the question?
if P is something to the solution and extended for IP. Yeah.
So this is the question. Here's some intermediate. Yes, I suppose so, but it may collapse. It's quite possible that you start. So what, for instance, if you start with Frege instead of extended Frege, then I think you get probably the same thing as you start with extended Frege. So there may be some collapses, but if you go higher up, and the higher up you go, then more likely things would collapse to the same process. But of course, we don't know things in each other.
Okay, so let's take further questions offline. Let's take Pavel again.